All right, welcome back to Statistical Analysis in Psychology. This is week 15, class number 1. And what we're going to do today is we are going to circle back to chapters 8 and 9. We had just finished with those, looking at t-tests for the 3 different situations. And now we're going to take a look at those same 3 situations, and we're going to learn how to generate confidence intervals for the results of those analyses. So thank you for joining me on this, our 7th class of the face-to-face shutdown. And today we are going to take a look at confidence intervals, which are a very useful tool, especially so for doing statistics in the real world. So not necessarily in a psychology laboratory, but more importantly, in the real world when you need to solve real world problems. So let's start with a few hypothetical examples just to kind of set the stage. So let's say that there's a monkey sanctuary out there, and this monkey sanctuary is a sanctuary for monkeys. So they have a whole bunch of monkeys in the monkey sanctuary. And let's say that one day, and this example is going to be a little apropos for the situation here. Let's say that one day there's a virus in the sanctuary, and they need to quarantine all the adult monkeys. So what this means is that all the adult monkeys get separated from the little baby monkeys, and now these little baby monkeys are left all alone. And the monkey sanctuary is concerned. They're concerned that these baby monkeys are not receiving any comfort. And somebody in the monkey sanctuary remembers Harlow's experiments on infant attachment and remembers that they used surrogate mothers to provide comfort for these infant baby monkeys. And now the question, though, becomes a real world question of how many of these terry cloth monkeys does this monkey sanctuary need to purchase for their baby monkeys? Because this is a real world problem now with real world constraints, such as budgetary constraints. So they might not be able to buy terry cloth monkeys for every single baby monkey. And they don't want to buy too many, in which case they're wasting money from their budget that could be spent on medical supplies for their adult monkeys. But they don't want to buy too few, in which case their baby monkeys are going to suffer because they're not getting the comfort that they need. So they need to know how long does a typical baby monkey spend with the terry cloth mother. And this is a very different question than what Harlow was asking, because Harlow just wanted to know, who do they spend more time with? Do they spend more time with the terry cloth mother or more time with the wire mesh mother? And for Harlow, it didn't really matter to answer his theoretical questions about infant attachment. It didn't really matter how much time the monkey spent with the terry cloth mother or the wire mesh mother. All that mattered to Harlow was, did they spend more time with one of the mothers? However, in the real world, it becomes a real question of how long do these monkeys spend with the terry cloth mother, because that's going to determine how many terry cloth mothers they need to purchase, how many they need to make in order that they can provide comfort for their baby monkeys in this situation. So let's take a look at another example that we're going to analyze today. So let's say that there was a car crash and it goes to trial. It was vehicular manslaughter, maybe, allegedly. And at the trial, there's a witness to the car crash, and the prosecuting attorney is asking, so how fast was the car traveling? And then all of a sudden just changes. How fast was the car traveling when it violently and egregiously smashed into the truck? And we know from Loftus and Palmer's studies that now that eyewitness memory is tainted. That eyewitness memory has changed. But let's say that that's the only eyewitness to the crime. What can this court do? Well, what they might do is they might say, all right, well, we're going to call up an expert witness. Maybe you, if you went into, memory research after you graduate here. So let's say that they call you up on the stand and they want to know how much was the memory affected, right? So how much did this woman overestimate her testimony because of the way that the question was asked? And notice again that this is a how much question. And as a research psychologist, Loftus and Palmer were not interested in how much. They were just interested in, is there a difference? Are the estimates of speed faster for the smashed into group than it was for the hit group? So they were just looking for a difference. But in this real world situation, it makes it very important to know how much was the speed overestimated. Was it by 5 miles an hour? Was it by 10 miles an hour? We know that it is overestimated. We know that it will have been overestimated because of how the question was asked, but by how much? That's the key question that is required in this real world context, and that's what a confidence interval is going to provide us with. All right, and then lastly, the last example, let's say that you graduate from IUSB, you become an industrial organizational psychologist, and one day you get a call from the very big corporation of America, and as it turns out, they've been sitting in their boardrooms having meetings, and they want to increase the accuracy of their workforce. They want to increase the accuracy with which their workforce operates, and they've heard about this study done on adult timeout, and they've seen that the adult timeout accuracy is increased in the 10-second condition compared to the 5-second condition. So the question for them becomes, if making those changes is expensive, if shifting from a 5-second timeout condition to a 10-second timeout condition is expensive, if they've already invested and they're already running the 5-second timeout condition, but now they want to change to the 10-second timeout condition, they know that those changes are going to be expensive because this is the real world. So they would need to know what increases in accuracy can they expect. So again, for the research purposes, for theoretical purposes, it was enough to know that there simply was an increase in accuracy, going from the 5 to the 10-second condition. But in the real world, they would need to know how much accuracy was there. Not just that there is a difference, but how much of an accuracy difference can they expect. So that sort of how much question is what we're going to be looking at today when we take a look at confidence intervals. So we're going to start off with a look at estimation. What is estimation and how do confidence intervals fit into that? And then we are going to take a look at each of the 3 different hypothesis tests and how to generate confidence intervals for each of those 3 different situations. All right, so let's begin with our overview of confidence intervals, starting with the idea of estimation. So estimation is, we've been doing this before when we went from samples to a population, but estimation is simply a process where you use a sample statistic, a statistic that you can measure, something that you can actually measure because you're working with a sample, and you use that to make an approximate judgment for the population parameter. So we measure a sample mean so we can estimate the population mean. We measure the sample standard deviation so we can estimate the population standard deviation. So that's the idea of estimation. It's that inferential process where you go from something that you can measure to approximate something about the population that you can't measure directly. So a very important concept, or 2 very important concepts for confidence intervals, which are a form of estimation, is going to be the point estimate and the interval estimate. So these are 2 different types of estimates. The point estimate is where you use a single number as an estimate of that unknown quantity. So usually when you ask a person in our culture to estimate something, if you tell them, well, guess how much, or can you estimate how much, usually what they do is they give you a point estimate. So if you were to ask somebody about their friend and you were simply to ask them, how tall is your friend? Usually what they would do is they would give you a point estimate. Usually they would say something like, well, she was 5'6". All right, so this is a point estimate. It's one number and it's your best guess, but it's a single number. It's a single point in this sort of possible range of estimates. So she was 5'6", very exact, single point. That's a point estimate. Another type of estimate is an interval estimate. And an interval estimate is where you use a range of values to estimate this unknown quantity. So again, if you were trying to guess or estimate the height of a person, you might use an interval estimate. And you might say, well, she was between 5'2" and 5'10". So this is also an estimate. You're also using something that you're using a quantity to approximate some unknown quantity, some unknown height of this woman, but it's a different type of estimate than the point estimate because it's a range rather than a single point. So these 2 different types of estimates have different types of characteristics. So the point estimate has very high precision, right? You know exactly what the estimate is saying. You know exactly where that height is being estimated at. It's 5'6", not 5'6.5", not 5'5" and 7/8, 5'6" exactly. So that's very high precision. Interval estimate, on the other hand, very low precision, right? So you got a range. It could be anywhere between 5'2" and 5'10", maybe 5'3", maybe 5'5", maybe 5'7", somewhere between 5'10", 5'2", and 5'10". So there's very low precision in the interval estimate. Now, the high precision that you get in a point estimate comes at a cost, and the cost is confidence. So that high precision gives you very low confidence because you are probably going to be wrong. The only way you're right is if that woman is exactly 5'6". If she's 5'7", your estimate is incorrect. If she's 5'6.5", your estimate is incorrect. If she is 5'6 1/4, your estimate is incorrect. So if somebody was to ask you, are you confident about your estimate of 5'6", you would have to say, no, I'm very low confidence, because even if she's a little off of 5'6", you're incorrect. So that high precision comes at a cost. It comes at a cost of confidence. You have low confidence. On the flip side, if you have low precision, you can have high confidence. And the confidence increases as the precision lowers. So if somebody was asking you, well, how tall was this woman? And you say, well, you know, she's between 5'2" and 5'10". They might ask you, is your confidence high? And you would say, yeah, my confidence is pretty high that she was between 5'2" and 5'10". But what if they wanted you to increase your confidence? What if they wanted you to have more confidence? What if they wanted you to be really, really sure? Well, then you might say, well, okay, to be really, really sure, I'm going to have to increase that interval a bit, because I'm really sure she was between 5'2" and 5'10". But if you want me to be really, really sure, then I would say she's somewhere between 4'6" and 6'4", right? So 4'6" and 6'4", now I'm really, really sure. And if they ask you, well, we need you to be really, really, really sure, you might say, all right, well, I got to increase that interval again. So now I'm going to go anywhere between 4 feet and 7 feet. Now I'm really, 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 really sure. And if they ask you, no, we need you to be really, 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 like super, extremely, massively, can't be wrong, absolutely sure, we need you to have massively high confidence. And you might say, well, I need to increase my interval one more time. If you need me to be really, 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 really massively, utterly, no way I can be wrong, totally confident, well, then I would say she was somewhere between 6 inches tall and 14.5 feet tall. I am super confident that she was somewhere in between that range there. So you can see that the lower your precision, the bigger the interval, the higher you can have your confidence. And what we're going to do today is, instead of using those loose terms of are you sure? Are you really sure? Are you really, really sure? Instead of using those loose terms, we're going to do what statistics does, and we're going to be able to put numbers on this. Specifically, we're going to be able to put a specific confidence level on this, where you can specify an interval, and instead of saying I am really sure, you can say I am 90% confident, or I am 95% confident. In fact, we're going to see a way to put an exact number on that. So if somebody says, I need you to be 99% confident that you are estimating her height correctly, you can say, you know what? Boom, here's your interval, 99% confident. That's what we're going to be doing today. So how do we get that confidence interval, that interval that we can be a certain degree of have a certain degree of confidence in? Well, it goes all the way back to the hypothesis testing. And what we've seen in hypothesis testing, and usually what happens in confidence intervals, is that they're only done after a significant result, after you reject the null hypothesis. Because once you reject the null hypothesis, once you find out that your sample is not in the body of that distribution of sample means, that it's in the tail of the distribution of sample means, well, what that means is that it no longer belongs to your previous population, which means that we now want to know about the new population that it belongs to. We want to estimate this new population. So once we find out that significant result, we now know that our sample belongs to this new population. it belongs to that treated population. And we want to know, what is the mean, for example, of that treated population? So because we know that the sample belongs to this new treated population, it is part of this population's distribution of sample means. But we don't know where in that distribution of sample means our sample came from. Maybe it came from the center, in which case it would be a very good estimate of the treated population's mean. Maybe it came from this portion, in which case it would overestimate slightly the treated population mean. Maybe it came from one of the tails, in which case it would really overestimate the treated population mean. So we can't be sure where our sample came from. So what we're going to do is we're going to make an interval so we can have a certain level of confidence that we estimated that population mean correctly. Now, before we go on, I just want to remind you that we're doing this through the distribution of sample means, because the distribution of sample means has the same mean as the treated population. So those two means are exactly the same. That's part of the central limit theorem. So if we can get the distribution of sample means, if we can get that mean estimated, we've estimated the population mean as well. All right, so concentrating on that distribution of sample means. Let's take it, we're going to stretch it out a little bit just for visual purposes. So the same distribution, just kind of stretched out so we can zoom in a little bit on that. And there we have our population mean. And I'm going to draw this dotted line down here. And any estimate that has that dotted line in the estimate is a correct estimate. So that dotted line represents the population mean. And if your estimate falls on that line, that means that you have correctly estimated your population mean. So if we measured our sample mean and just by chance it happened to be the same as the population mean, if we had this point estimate and just by chance it happened to line up directly with the population mean, well, then we successfully estimated the population mean. We were successful. We were correct at estimating it. But this usually doesn't happen. But let's take a look at what happens when we choose a very specific interval. So we choose a very specific interval here by taking a look at the body of this distribution of sample means and the tails. So the body is a certain percentage of this distribution of sample means. So let's say that we had an alpha level of 0.05. So we got 5% total in the tails, we got 95% in the body. What happens when we make our interval as wide as the body of our distribution? Well, if our point estimate, if that mean, that sample mean, so that dot with the M in there, that's your sample mean. If we had a sample that had a mean the same as the population mean, and we put this interval around it, well, we've correctly estimated the population mean because the population is contained within this interval. The population mean is inside of that interval. So that's the uninteresting case where we got it correct with the point estimate. But what happens if we missed with the point estimate, like right here? So our point estimate, our sample mean, overestimated the population mean. Well, the point estimate in this case missed. So that high precision, again, came at a cost, low confidence. We can't be confident that our sample mean is going to be the same as our population mean. But notice what happens when we still have that same interval. That interval, that's the width of the body of our comparison distribution. When we put that interval in there, notice that the interval covers the population mean. So this would be a correct estimation of the population mean, meaning that the population mean is in this interval. So this would be a correct estimation. What happens if our sample mean underestimates the population mean? Once again, the point estimate, we miss. However, the interval estimate, if it's as wide as the body of our comparison distribution, so not including the tails, but just the body, notice again that the interval contains the population mean. And the same thing if our sample mean came from that part of the distribution, or this part of the distribution, or this part of the distribution, or over here, or over here, or from this part of the distribution, or if it came from this part of the distribution, or this part of the distribution, or this part of the distribution. So notice that so far, none of those intervals have missed the population mean. Some of them have it on their low end, some of them have it on their upper end of their intervals, but all of them cover that interval in some way. In fact, it's only this one here that has missed the interval. It's only this one here where the interval has missed the population mean. And this is the first sample with a sample mean that has come from the tails. And when you make a interval as wide as the body of your distribution of sample means, the only way you miss the population mean as in terms of an estimate, the only way you miss that population mean is if your sample mean just happened to come from the tails. And the probability that your sample mean is going to come from the tails is the same as the size of your tails. So the only way that we're going to miss this estimate in this example is if our sample mean came from the tails, 5% of the distribution is in the tails, so we only have a 5% chance of getting a sample that's from the tails. Therefore, we only have a 5% chance of our interval missing the estimate, and hopefully you can guess the ending here. If we have a 5% chance of our interval missing the estimate, then we have a 95% chance of our interval getting it correct. If we have a 95% chance of getting it correct, we can be 95% confident that we're going to estimate it correctly, hence the 95% confidence interval. So you increase or decrease your confidence by increasing or decreasing the tails. If you decrease the probability that you'll miss, you increase the probability that your estimate will hit. So again, if we want to make sure that we are 99% confident, we want to have tails that are only 1% of the distribution. So we only have a 1% chance of getting a sample from that tail missing the population mean on our interval, meaning that we have a 99% chance that we don't miss, and we can be 99% confident. So we're going to do just a really quick little peek behind the curtains before we go to SPSS to do the math for real. But just so you know how this is all kind of built up, and just so you kind of know the pieces that go into a confidence interval, confidence intervals are based on the general equation for a t-statistic. So we're using the t-statistic, but the t-statistic in general was equal to the sample mean minus the population mean, and all of that divided by the estimated standard error. Notice that what we want to estimate is in this equation. We want to estimate the population mean. So we can isolate, using algebra, we can isolate for that population mean. And this equation becomes the population mean equals your sample mean plus or minus your t-statistic multiplied by your estimated standard error. And that t-statistic is your critical t-score. It's your cutoff t-score for the tails of your distribution. So let's take a look at this equation, and we'll put it here in this visual representation. So we're going to hone in on this, focus in on this interval right here. So this has all the parts of the confidence interval relation with the population distribution expressed in that equation. So the population mean is what we're trying to estimate. So that is what we're trying to estimate. We want to know for this unknown new population, what does that population mean? So that's what we're trying to estimate. Our best guess is the sample mean. So we know that our sample belongs to this population. We don't know where, but our best guess for the population mean is the sample mean. So if we needed to do a point estimate, that would be our point estimate. The sample mean is our point estimate. It's our best single guess. But we don't want to just do a point estimate. We want a range. So how do we determine that interval? Well, this plus or minus is the interval. So plus or minus t times the estimated standard error, that is the length of your interval. So the plus side gives you the positive side of the interval. The minus part gives you the minus side of the interval, or the lower side of the interval. So we can put this into the symbols that we have there. So population mean equals your sample mean, and all of that is plus or minus your cutoff t-score multiplied by your estimated standard error. So that's your look behind the curtain. That's just to kind of show you what we want to, components are of a confidence interval. Also, this is the form that you want to get your confidence interval into. You want to get your confidence interval into a point estimate plus or minus the arms of your interval. So a point estimate plus or minus this and that. And this is typically what you hear, especially in the news given election seasons. You'll often hear that, oh, so-and-so's approval rating is 40% plus or minus 3%. The polling reveals that the lead is now 10% plus or minus 1%. So what they do is they give you that point estimate, and then they give you that plus or minus. They let you know how much higher and how much lower it might go. So that's the format that we want to report our confidence intervals in. We want to report it in that here's our best guess, point estimate, plus or minus, here's the upper and lower ranges. All right, so now that we know what we're doing and what confidence intervals are, we are now going to turn to a little in-class practice, a little follow-along practice on how to actually calculate these confidence intervals. And before we begin, I just want to let you in on a little secret. So as it turns out, you are about to find out that you've been in a little bit of a Dorothy in the Wizard of Oz situation, because you have been asked to calculate confidence intervals in some of your homework assignments. And it was good to learn how to calculate those confidence intervals. And, it's good to struggle through that and kind of learn the ins and outs of what a confidence interval is. But what we're going to find out today is that this entire time, you've actually been calculating confidence intervals. So forgive me for not introducing this a little bit earlier. I didn't want to overwhelm you with all this knowledge. But as you're going to see, the way to calculate a confidence interval is exactly the same as conducting a t-test. That's why we were waiting until we were done with t-test. So without further ado, I'm going to play Glenda the Good Witch. We're going to fast forward to the end of the movie, and let's get going with calculating confidence intervals. All right, so once again, when we took a look at Harlow and his monkey study, Harlow was only interested in whether there was a difference, whether there was preference for one mother or the other mother. However, in the real world, a place like the Monkey Sanctuary is not interested in whether there's a difference. They need to know, how much money do we need to set aside to buy terry cloth monkeys for our baby monkeys? They need to know. They have a budget. They have real world concerns to deal with. They want to know not that the monkeys spend more time with the terry cloth mother. They want to know how many hours do these monkeys spend with the terry cloth mother. Is it 15? Is it 18? Is it 19? How many should they buy so that they can spend as little money as they can, but still make sure that their monkeys are cared for? That's what they need to know. That's a confidence interval question. All right, so if you recall, we've gone through this a few times. So I'll just kind of briefly give you the synopsis. It was a classic study of infant attachment. There was two surrogate mothers that these monkeys had access to. One was a terry cloth mother. It was soft. It provided no food. The other one was a wire mesh mother. It was hard, but it provided life-sustaining milk. And in a typical day, the infant spent a total of 18 hours clinging to one of the two mothers. And if there was no preference between the two, they would spend 9 hours with each mother. However, the typical monkey spent 15 hours per day with the terry cloth mother, indicating that strong preference for the terry cloth mother. We looked at a sample of 9 infant monkeys that averaged 15.3 hours per day with the terry cloth mother. And we've already analyzed this. Is the result sufficient to conclude that the monkeys spend significantly more time with the softer mother than would be expected? Yes, they do. We have already done that t-test. We've already found that it's significant. We already know that they spend more time with the terry cloth mother. Now we're going to answer the monkey sanctuary's question, not whether they spend more time with the terry cloth mother, but how many hours per day do they spend with the terry cloth mother? So we're going to compute various ranges of confidence intervals for one reason, to show you how to do this for various different ranges, but also to kind of illustrate the principle of how these confidence intervals change as you compute different ranges, and also to kind of give you insight into one of the applications for this. Different people need different levels of confidence in order to make their decisions. So somebody might say, you know what, I want to make sure that all the monkeys have access to surrogate mothers, but I only need 95% confidence in order to make my decision. I don't need to be 100% sure. You can never be 100% sure, by the way, but they need 95% confidence because they're erring on the side of the monkeys. Then you might get an accountant that says, look, you know, I don't want to spend too much money on this. I really want to make sure that we protect our budget. So I don't need to be 95% sure. I just need to be like 80% sure. I care about the monkeys, but I'm good with making an error. You know, I'm good with a 20% chance that maybe we don't buy enough terry cloth mothers. And then you might get somebody else that says, oh, no. Like I can't even risk 5%. I can't, I don't even want to go as low as 1%, but I guess I have to. I need to be 99% sure. So we're going to calculate all three of these. We're going to calculate a 95, we're going to calculate an 80, and we're going to calculate a 99% confidence interval as well. All right, so what we're going to do now is we're going to go to SPSS. While we're doing this, while I'm setting up here, I'm just going to mention that the screenshots are available on Canvas, and you can follow along in the video. We are, though, going to go pretty fast. So if you need to, pause the video while you set up your confidence intervals, while you set up your t-test, and join me again when it's all done and ready to go. And hopefully that way we can cover this and you can learn at your own pace. But again, feel free to pause the video if you need to. Just know that all the screenshots are there and they are available. And as well, you know, feel free to pause the video if necessary. All right, so without further ado, I will just mention that if you haven't already, sign into Canvas. And the data that we are looking for is that data right there. So it's the same data that we've used before for this particular study. And also, if you haven't already, you are going to want to open up SPSS, and I've done that already. So without further ado, let's get going on this particular confidence interval. All right, so the first thing is we're going to close this welcome box, and let's set this up real quick. So we're doing a single sample t-test. So we're going to take our terry cloth monkey data, and we are going to paste that into our data editor here. var 00001, horrible name. We're going to change that to Terry. And then we are going to run this as a t-test. And we're going to go to Analyze, we're going to go to Compare Means, one sample t-test, and we are going to do something just a little bit different. So this is where I'm going to pause. Hopefully you've set this up like we have it right now. If you haven't, again, pause the video and come back here when you've had it set up. But this is one thing that we're going to do, and I'm going to make a point about it right now. In this particular question, they were asking for how much time do the monkeys spend with the terry cloth mother. They didn't want to know what is the difference in terms of how much time they spend, but they wanted to know how much time do they spend. So for that purpose, if they were asking for how much time do they spend, to make our lives easier, we're going to leave the test value at 0. So make a note of this. In a single sample t-test, if the question is how much of something is there, keep your test value at 0. If on the other side the question was, what is the difference? How much more? How much less, right? If that's the question, if they're asking for a difference, then put in the test value that is your null hypothesis mean. So if they were asking how much more time do they spend with the terry cloth mother, we would put in the test value of 9. However, recall that the question wasn't how much more time they spend, but how much time they spend. So because of that, we're going to put in a test value of 0. So just make a note of that. If you're asking for how much of something in a single sample t-test confidence interval, leave your test value at 0. Otherwise, if it's a difference, if it's how much more, how much less, how much different, what was the increase, what was the decrease, then put in your test value the way that we did before. All right, so we're going to keep our test value at 0. And then the last thing we'll do is we're finally going to click on this little options button here. You might have been wondering what that was about. And this is where you find your confidence interval percentage. So the default here is 95%. That is by far the most common confidence interval. So we're going to leave it there as is, and we're going to hit continue. And whoops, we're going to pop Terry in here into our test variables. I got so carried away with confidence intervals, I forgot some of the basics. So we got Terry in here as our test variable. We got our test value at 0 because we're interested in how much time do they spend with the terry cloth mother. Options over here, confidence interval percentage at 95%. we hit OK, and we get the same output that we've been looking at all this time. But what I want to do is I want to draw your attention to this little section over here where it says 95% confidence interval of the difference. There it is. There's your 95% confidence interval. Now, we were going to calculate 3 confidence intervals. So let's go back and do that. So we can go right back here to analyze. We go back to compare means, back to one sample t-test. Nice thing about this is if you have to calculate multiple confidence intervals, it's already set up for you. All we need to do here is go into options, and we're going to change this to the confidence that they were asking for. So that second person from the monkey sanctuary asked you for an 80% confidence interval. So we change that to 80. We hit continue. We hit OK. And notice that SPSS is being very friendly because it added the output right below our previous test, and also it labels it very nicely. So it's very clear. This is the 80% confidence interval. This one up here is the 95% confidence interval. So there's no chance that you're going to confuse yourself. All right, and then the last one, we go to analyze, compare means, one sample t-test. Again, already set up. We hit options. The confidence interval percentage that last monkey researcher wanted was a 99% confidence interval. We hit continue. We hit OK. And we see that we have calculated a 99% confidence interval. All right, so that is the SPSS output. So now, like we've done before, we're going to take a look at how to actually analyze and interpret that SPSS output. So we're going to focus in on the first one. We're going to focus in on that 95% confidence interval. So let's zoom in there. And you're going to notice that the numbers here are a little bit different. I'm gonna help you out with that in just a moment. But you're going to notice that the numbers are a little bit different. Don't worry about that right now because we're going to go through the things that you need to know, and then I will adjust that as required. So the first thing to do is we're going to look for the component parts of our confidence interval. So the first thing to do, and I know I'm not going to mention this, although I am, because I know you're already aware of it. The first thing to do is to check your one sample statistics. Make sure you got the right number of scores. Make sure that the mean is correct. I'm taking a look at that right now. It's all good. So we have the confidence to go forward. In your confidence interval equation, in that population mean equals sample mean plus or minus your t-statistic multiplied by your estimated standard error, that estimated standard error is right there. That's where you can find that component of your confidence interval equation if you needed to do this by hand. The degrees of freedom will let you know where you can look up your confidence interval, where you can look up your t-statistic for your confidence interval in your t-statistic table. So that will help you find that those cutoff scores if you were doing this manually. You can tell by my explanation of confidence intervals right now that it's probably not a good idea to do it manually if you can let SPSS do it, and lo and behold, yes, you can. So this is the 95% confidence interval of the difference. And what you're going to notice right now is maybe this wasn't the greatest idea, but I did this with the difference value first. So you can see up here in the test value, in the one sample test, in that bottom table, you can see that the test value is equal to 9. Your test value should be equal to 0. So what I need to do right now is, and mentally just follow with me, is I would need to add 9 back into the mean difference and the lower and upper estimates. So just kind of bear with me on that. Sorry that we had this little mix up here, but we're going to do the best that we can with it, and we're going to carry on. So here we have the 95% confidence interval of the difference. Your point estimate for this confidence interval is the mean difference right there. Your mean difference will say 15.3 because you did it the easy way and you took out that test value initially. So your mean difference should say 15.3. Your lower and upper values should say 11.3 and 19.29. So we have the center portion. That's your mean difference. That's your point estimate, 15.3. Then we have the lower bound and we have the upper bound. So we have all the information that we need for our confidence interval. So how many hours per day do the monkeys spend with the terry cloth mother? Well, we need to get these confidence interval data that we just calculated, and we need to put it into a form that people can understand. So these confidence intervals, the way that I calculated it, it's the difference between the actual population mean and the assumed population mean. So when we add 9 back in, it's just the actual population mean. And it gives you the lower and upper bounds. So we're going to need to use some logic, and we're going to need to use some math to put it into that point estimate plus or minus upper and lower bounds format that we want to get it to. So we have our point estimate. That is the mean difference. I'm going to add 9 back into that. So your mean difference is 15.3. That's your mean difference. We then have our lower bound, our lower limit, which is 11.3, and our upper bound, which is 19.3. The way that you can convert that into a format that we can understand is we have our mean difference, we have our sample mean there of 15.3. Again, that is always your point estimate. And that is our best guess, 15.3. What you do in order to find the plus or minus with that is there's a number of different techniques you can use. This is the one that I always recommend. You take your upper bound, right? You take that upper bound, that 19.29, and from that you subtract your point estimate, 15.3. So upper bound minus point estimate will always work regardless of whether they're negative or positive or anything like that. Upper bound minus your point estimate will get you that plus or minus value that you're looking for. So when I calculated these, that was my point estimate, 15.3. That's my best guess. How many hours are the monkeys going to spend with the terry cloth mother? 15.3 hours. That's my best guess. Am I confident? No. Can I calculate a 95% confidence interval? Absolutely. I am 95% confident that the monkeys will spend 15.3 hours per day plus or minus 3.99 hours. And that 3.99 was found by taking the upper bound minus your point estimate, and that gives you that plus or minus 3.99. If you only need to be 80% confident, then your estimate is 15.3 hours plus or minus 2.42 hours per day. And notice that the 80% confidence interval is narrower. So you don't have as much confidence, but you have more precision. And then for the person that needs to be 99% confident, well, there's their range right there. 15.3 hours plus or minus 5.81 hours per day. So those monkeys can go anywhere up to 21.1 hours per day with the terry cloth mother. So if you want to make sure that you have enough terry cloth mothers, you want to be 99% sure that you have enough terry cloth mothers for the monkeys, you would have to go to the upper limit of that 99% confidence interval and buy enough terry cloth mothers so that each monkey can spend 21 hours a day with that terry cloth mother. So you don't got to buy a mother for every monkey, but you do have to buy enough so that they can each spend 21 hours with the terry cloth mother. All right, that was a single sample t-statistic. What we're going to do is we're going to continue on, and we're going to take a look at the other two remaining t-tests and how to generate confidence intervals for those. So let's keep going. And our next example, once again, you can find the data in that Excel sheet. This one is going to be about the eyewitness memory. So once again, if in a court case, a prosecuting attorney asked a question in an incorrect way, that eyewitness's memory was changed. It was affected. And as a psychologist, we're very interested in the fact that it was affected. But as a lawyer, as a judge, as this person who might be going to jail, they're not interested that the testimony was overestimated. They're interested in by how much, how many miles per hour. So to answer that, we're going to go back to the Loftus and Palmer study. So once again, it had two different groups. One was asked, how fast were the cars going when they hit each other? The other one was asked, how fast were the cars going when they smashed into each other? Two different sets of subjects, independent means, t-statistic. And now let's say that the judge was, calls you in as an expert witness, and you are asked to how much faster were the estimates for the smashed into group? How many miles per hour faster were the estimates for the smashed into group? And you're going to compute a 95% confidence interval. You're going to compute an 80% confidence interval, and once again, a 99% confidence interval. So we're going to continue on. So again, we're going to go through this pretty fast. The screenshots are available in the PowerPoint as well. But if you need to pause the video at this point, set up your SPSS editor. We're doing a independent means t-test, and I'm going to do that rather quickly right now. So the first thing I'm going to do is I'm just going to clear out all of my previous data, and then we're going to go back to our Excel sheet. And let me see, did I do that for this one? Yes, I did. So just to kind of speed things along, here's a properly formatted data set that I prepared earlier in the day. I feel like one of those cooks on a cooking TV show. So we're just going to paste that right in there, and we are going to call this one speed. So var 002 is speed. Var 0003 is the group. So what kind of question were they asked? And we're going to go to analyze. Compare means is going to be the independent samples t-test, and speed is going to be the test variable. Group is the grouping variable, and we are going to define the groups, and the groups are smashed, and the second group is hit. And we're going to hit continue. And normally if we were doing a t-test, we would just hit OK and we would go on. However, now we're going to go to options. And in options over here, we can see that we have the option for a 95% confidence interval. So notice that, again, the default is 95% confidence interval. So always double check that to make sure that you're getting the interval that you want. We want a 95% confidence interval. We hit continue. We hit OK. And we see our typical output for an independent means t-test. But notice right down here, 95% confidence interval of the difference. So we computed our 95% confidence interval. Let's go back and do the 80%. So analyze, compare means, independent samples t-test. All set up, which is great. We're going to hit options, change that 95% down to 80%. Hit continue, hit OK. And notice that we now have an 80% confidence interval of the difference. And then finally, we are going to go to, it was 80%. So finally, we are going to go back and do one more, which is our 99% confidence interval. So we're going to go to analyze, compare means, independent samples t-test, hit those options, 99% for the lawyer that needs to be really sure. We hit OK, and we have a 99% confidence interval computed. Now notice that this time we are computing of the differences, right? We are computing confidence intervals of the difference, and that's because of the question that was being asked. So they didn't want to know how much did this person estimate the speed was. They wanted to know how much more was their estimate increased because of the question that was asked. So always keep an eye out for whether they're asking how much more something is or how much something is. So what's the increase or what's the value? What's the absolute amount or how much did it change? Always keep an eye out for that, because sometimes, especially in the single sample t-test, you're going to calculate the absolute amounts. Sometimes you're going to calculate the difference. In an independent means t-test, you're calculating the difference. So in this case, once again, you would want to check your table number 1 to make sure that you entered your data in correctly. So feel free to pause to do that at this moment. However, we're going to keep going. And again, remember that we're looking at that equal variances assumed row. And if we were doing this by hand, those degrees of freedom right there would help us with the t-statistic table to find our cutoff scores. And we will multiply those cutoff scores by the standard error of the difference to find the arms of our confidence interval. However, thankfully, SPSS does it for us. So here we have the 99% confidence interval of the difference. So we're doing the 99% one here. And notice once again that we have our point estimate. So the point estimate is the mean difference. So again, make a note of that so you know where to find it. Point estimate is the mean difference. And what that means is that our best guess of how many miles per hour the eyewitness overestimated in their tendency is that mean difference right there, 6.8. That is our best guess. That's our point estimate. However, the 99% confidence range goes all the way from a low range of minus 4.6 miles per hour all the way to the high point of 14.06 miles per hour. So that's the information that we have from SPSS, not in the format we want. So we're going to have to take that and we're going to have to change it into the format that we're looking for. So we want to know how much faster are the estimates for the smashed into group. So this confidence interval, we are given the difference between the smashed into population mean and the hit population mean, and we are given the lower and upper bounds. And what we need to do right now, that's what SPSS gives us. We need to use a little logic, we need to use a little math, and we need to put it into that format of point estimate plus or minus that range. So once again, the point estimate, your mean difference. That's our best guess. The plus or minus value you can find from your lower and upper ranges. Again, there's a number of different ways to do this. The way that will always work is your upper value minus your point estimate. In this case, the upper value minus the mean difference. So 14.06 minus that 6.8. And that's what we would do to calculate that plus or minus value. And if we did that for the intervals, this is what we would find. So this is an interesting case because we're going to have that no difference line. That no difference line is the difference between overestimating and underestimating. Everything on the right of that line, overestimated eyewitness testimony. Everything on the left of it, underestimated eyewitness testimony. That's going to come up when we take a look at our 99% confidence interval. So if the judge asked you, as a witness, as an expert witness, how much did this eyewitness overestimate their testimony, and he wants a point estimate, you would say, all right, well, my best guess, my best estimate, 6.8 miles an hour. And if one of the attorneys came up to you and said, objection, you need to be 95% confident. We need a range that gives us 95% confidence. Well, then you would say, all right, 95% confidence, 6.8 plus or minus 5.35 miles per hour. That's my 95% confidence range. And then if the defense lawyer said, no, we don't need to be that confident. No, we only need 80% confidence. What's your 80% confidence estimate? In that case, you would say, well, 80% confidence, it was 6.8 plus or minus 3.41 miles an hour. So all the way down to 3.4 miles an hour, but potentially all the way up to 10.2 miles an hour. And then if the judge intervenes and says, look, in order for your testimony to be entered, we need a 99% confidence interval. We need to make sure that you are 99% sure in the estimates that you're giving us. Then you would say, all right, well, 99% confidence interval, there you have it, 6.8 miles per hour, plus or minus 7.26 miles per hour. And notice that this confidence interval contains that no difference. This confidence interval contains the estimate of 0 miles per hour overestimated. In fact, it contains negative miles per hour overestimated. That's also known as underestimation. So if the judge turns to you and says, can you be 80% sure that the testimony was overestimated? Because the entire confidence interval is on the positive side, the entire 80% confidence interval is on the positive side, you can look at that judge and say, yes, I am 80% confident that this eyewitness overestimated their testimony. And if the judge came back and said, are you 95% confident that they overestimated their testimony? You can say, yes, I am 95% confident. But if the judge asks, are you 99% confident? Because your 99% confidence interval contains that estimate of 0 miles an hour and a few estimates below 0 miles an hour, you cannot be 99% confident that the witness overestimated their eyewitness account. So as you can see, a lot of light can be shed in a real world situation using these confidence intervals. All right, last one we're going to do. So this is, again, the practice problem. Data can be found in that Excel sheet. And this one is going to take a look at the timeout, the adult timeout situation. So as a psychologist interested in behavior, I would mostly be interested in whether 10 seconds is more accurate than 5 seconds as a timeout condition, because I just want to know how our minds work. In the real world, however, there's other things to consider, such as how much is this going to cost to implement? And is the increase in accuracy worth the trade-off that they're going to have in terms of the cost to implement it? So those are the types of real-world problems, again, that we're addressing with these confidence intervals. So again, we go back to the original data. We go back to the original study where they put adults into a 5-second timeout condition, and then the same adults into a 10-second timeout condition and measured their accuracy in each conditions. That's a dependent means t-test. So we're going to see how to use that dependent means t-test now to generate confidence intervals. So we already know, because we've done this analysis before, that subjects were more accurate in the 10-second timeout condition. We already know that they were more accurate in that 10-second timeout condition because we've already run that statistic, that statistical test. But now we want to know how much more accurate were they in that 10-second timeout condition. And again, we're going to compute our 3 confidence intervals. Now we keep going back to the same ones. We keep doing a 95%, 80%, and a 99% confidence interval. These ones are the 3 most common confidence intervals that you'll come across. 90% is also pretty confident, but or pretty common. But note that you can compute any confidence interval you want. You can compute a 17% confidence interval. You can compute a 99.9% confidence interval. You can do anything between 0 and 100. You can't do, well, you can do 0. That's the point estimate. But you can't do 100. That's an infinitely large confidence interval. But anything in between you can do. We just happen to choose the ones that most often are used in psychology. All right, so because of the description of the experiment, because of the setup of the experiment, we know we're doing a dependent means t-test. So let's get going on that. Once again, screenshots are available in the PowerPoint. Once again, I'm going to do this pretty quick. So if you need to pause the video, feel free to do so. Set up your independent means t-test and join me again when you are ready to go. So before you click that OK to do your t-test, make sure that you pause so that you can see how to do the confidence interval for this particular t-test. All right, so we have our data. Paste that in. Change the variables. We got second 5. We got second 10. Data view, analyze, compare means, paired samples t-test, and we are going to put in 5 seconds as the first variable, 10 seconds as the second variable, and then I'm going to do another one down here where I put in 10 seconds as the first variable and 5 seconds as the second variable. And I'm going to show you why I'm doing that in just a moment. So I put it in both ways. And the reason for this is that one of these ways is going to give me a negative difference. Another way is going to give me a positive difference. So I know that the 10-second timeout condition is more accurate. But what I don't know is which way SPSS goes. And it's very difficult to remember. So I'm going to load them both up. And then we're gonna deal with this one here. So we're going to go here to options. And again, we want a 95% confidence interval. So that's a confidence interval that is already listed there by default. So we just double check to make sure that it's true. We hit continue, we hit OK, and we have our outputs here. So notice that our first output, seconds 5 minus seconds 10, that gave us a negative change. That means that the 5-second condition is minus 7% compared to the 10-second condition. That means that the 10-second condition has a minus 7% decrease compared to the 5-second condition. Minus 7% decrease is an increase, and that's just way too much mental gymnastics for me to do. So that was pair number 1, and I've decided that we don't want to do pair number 1. We're going to do pair number 2. So now that that decision is made, I'm just going to go back here real quick. We're going to go to analyze. We're going to go to compare means. We're going to go to paired samples t-test, and I'm just going to get rid of pair 1 because I don't like pair 1. And we're just going to go with pair 2. And now we have a 7%, positive 7% change is a positive increase. That makes more sense to my human brain, so that's the one we're going to go with. So we've done the 95% confidence interval of the difference. So we go back, analyze, compare means, paired samples t-test. We click on options again. This time we're going to do that 80% confidence interval. So we change that confidence interval to 80, hit continue, hit OK. We now have our 80% confidence interval of the difference. And then the last one we're going to do, analyze, compare means, paired samples t-test, go to options, enter in 99 for our 99% confidence interval, hit OK, hit OK once again to run the analysis, and we have our 99% confidence interval. So we just calculated 3 confidence intervals in the space of about under a minute. Thank goodness we got SPSS to do all this for us. All right, so we've calculated our confidence intervals. Now it's time to find out where we can find the information. We're going to go back to that 95% confidence interval of the difference. And again here, sorry about this, I got the negative numbers on these screenshots. Don't worry about it. Everything is the same numbers. It's just flipped with the negatives. So we're going to proceed as if I did this the correct way. And I apologize for this. You know, with the face-to-face shutdown the way that it is, we're going to have to deal with and do our best as we can. All right, so we're looking at this line down here. Again, remember, check your top tables. Make sure that you've entered in your data correctly. And if you're doing this by hand, there's your standard error of the mean. There's your estimated standard error. There's your degrees of freedom with which you can go to your t-statistic table to look up your cutoff scores. But thankfully, SPSS has calculated all of this for us. So SPSS has given us our upper and lower bounds. Your upper limit is going to be 11.61. Your lower limit is going to be 2.39. I can do those mental gymnastics. You don't have to, so remember that switching of the order of time, second 5 and second 10 can help you not have to do those gymnastics. But importantly, the information that we need is there. So the point estimate, the amount of increase in accuracy is given to you right there. So you should have 7% as your increase in accuracy, and that is how much accuracy you get more in the 10-second timeout condition. Your range, though, your upper and lower range is given to you right here. So your upper range is 11.61. Your lower range is 2.38799. That's the information that SPSS has given us. However, we want to put that into a format that is more understandable. So what are these confidence intervals of? Well, we have the difference between the 10-second population mean and the 5-second population mean, and we have our lower and upper bounds. So now we got to use a little logic and a little math. So the center of our interval, our point estimate, our best guess at how much more accurate the 10-second timeout condition is right there. It's the mean difference, and in this case, it's 7%. And then to find that plus or minus value, we take the upper bound and we subtract the mean difference. So for your case, you're going to take 11.61 and you're going to subtract away 7. But also notice that even if we did it with this data right here, if you took minus 2.38799 and subtracted from that negative 7, you would get the same answer. You would end up with 4.61. So that's what I was talking about. And maybe it's a good thing that we had this little mix up here. That's what I'm talking about, how the upper minus your point estimate will always give you that correct plus or minus value. So that's the move, the mean, that right there, that's your point estimate. And then you use your upper minus your mean to give you that plus or minus value. And if you did this for the 95% confidence interval, well, first off, if we did the point estimate, if they simply said, you know what accuracy can we expect if we go to what increase in accuracy can we expect if we go to the 10-second timeout condition? You, if you were called into that board meeting, would say, you know what, 7%. You're going to see a 7% increase in accuracy. And if somebody said, you know what, I need a little bit more confidence than that. Are you confident in that estimate? You would say, no, that's a point estimate, 7%. That's my best guess. And if they said, look, I have savings invested in this company, I got stock options that I just can't be willy-nilly with, I need to be 95% confident in the increase in accuracy. You would say, all right, 95% confidence, 7 plus or minus 4.6%. So you can expect increases up to 11.61, but at least I'm 95% confident that you are at least going to get an increase in accuracy of 7 minus 4.61, which is 2.39. So that would be the 95% confidence interval. Somebody else in that board meeting might say, you know what, I'm young, I like risk, I got time to recover if my investments don't pan out. I don't need to be 95% confident. I only need to be 80% confident. And you would tell that person, well, 80% confidence, you can expect an increase of 7% plus or minus 2.79%. And then if that third hand goes up and the person says, look, I've got money invested in this company too, but I borrowed from the wrong people. And if I don't pay them back, they're going to break my legs and they're going to do other horrible, horrible things to me. So I can't be 80% confident. I can't even be 95% confident. I got to be 99% confident that I'm going to see an increase. Can you do that? Well, you would say, well, yeah, 99% confident. You're going to see an increase of 7% plus or minus 6.71%. So you're going to be, I'm 99% confident that you are at least going to see an increase of 0.29%, maybe all the way up to 13.71%. And notice that all of those estimates are on the positive side. All of those estimates are increases in accuracy. So you are 80%, 95%, and 99% sure that moving to 10-second timeouts will increase the accuracy of the workforce. All right, so that was a lot. There is your confidence interval overview. And what I'm going to mention now is homework assignment number 13. That is available. That is a Canvas Excel homework assignment. So it's one of the few that is not available in my lab. It's available through Canvas. It's an Excel sheet. You download it. It's automatically updating. So it'll let you know whether you got it correct or whether you got it incorrect. Feel free to do it as many times as you need in order to earn that 100%. And upload that. I moved the due date on that due to the mix-up with exam number 3. So that is now due Monday, April 27th by midnight. And also just wanted to mention that for a little bit more practice, there are a few more questions left on the confidence interval Excel sheet that we used today for practice. And you have the questions in the Excel sheets that have been uploaded. So you have those questions, you have the answers as well. So work through those if you need a little bit of extra practice on these confidence intervals before tackling your homework. But also remember, you have unlimited tries at your homework as well. All right, so that is our look at confidence intervals. Thank you for bearing with me through some of these mix-ups. But again, that's just the way that things are these days with the face-to-face shutdown. However, again, go back and review some of this. If it was a little quick, feel free to pause the video at any point to let it all sink in. We have been doing confidence intervals this entire time. So it's just a t-test with a new look at some information that was put out that was ignored before. And again, identifying that point estimate, that best guess, that mean difference, and then using the upper bound minus your point estimate to give you that plus or minus value for your confidence intervals. So that is it for today. Thank you so much for joining me for this look at confidence intervals. I will see you next time when we introduce ANOVAs, our final hypothesis test. But other than that, we are done. Thank you so much for joining me today. Keep yourself safe, and I will see you next time.